All right, let's get started. Okay, so in our last lecture, oh, yeah, I should remove this, right? So we're all, yeah, we finished that. So in our last lecture, we finished talking, we started talking about AEP, right? So the asymptotic equipartition property, right? And here are some definitions. So we define a memory-less source as follows, right? So I have a sequence from x1 till xn and so on, right? We assume that they are independently, identically distributed, right? So this is very important. So we'll start from here, right? But later on, we're going to extend the concept to other type of sources that with memory, okay? And then we introduce a weak law of large numbers, right? So for the main part in our class, so we'll just use a weak law of large numbers, right? So yeah, this basically tells you that, okay, so if we have a sequence of random experiment, right, and then if we compute the mean of those, then the mean of those would be very close to the expectation of each random variable, okay? And this convergence is, so the limit is outside, so it's converging probability, right? And then we'll give you the definition of the what is a typical set, right? So we have two definitions of typical set. So one definition is given by this. So it basically defines empirical PMF, right? So the empirical PMF is defined as follows, right? So here we just count the number of i's, that xi equals to x, right? And then we normalize the total number of random variables, okay? And so, yeah, this is a kind of probability, but it's not, right? So just count the number. It's a combinatorial kind of structure that just count the number of x here, okay? And when n will become very large, obviously, this will be very close to the probability, right? When n is small, obviously that will not be any close, right? All right. So, and based on this definition, so we define if the pi, right, this empirical PMF is very close to the actual PMF, then we say this sequence of x is in the typical set, or it is typical. Okay, so so this is kind of a very convenient way to define the typical set. So it's not exactly the strong typicality. So this entropy typical set is normally called a weak typicality. Okay, so this technically is not strong yet. Strong, I mean, because of this. Okay, so yeah, but we don't need to worry too much about it. I think one thing we need to somehow remember is that so this work on each value of the PMF, right? So we can, roughly speaking, we can think this as PX, more or less, right? But for the entropy typical set, which is defined in this way, right? So basically it means that the self-entropy of the sequence X is very close to the entropy of the sequence, right? So because we're considering a in IID sequence, right? So this n doesn't matter, right? We can put this n here inside, right? So it's equal to the entropy of the whole sequence, right? Because they're IID, right? So this is kind of on an average sense, right? Because this guy is an average of the individual probability, right? So basically, here, we're working on some kind of average sense, but this one we're working on each individual probability, right? Therefore, you can see, so this should be stronger than that. Does that make sense? Okay. And another beauty of that is, somehow, this is kind of a counting argument, a counting process, right? So the number of x's on the numerator and right over n, right? So basically, we can kind of count, each type here. Each type basically I mean for each of the value here. Each of the value here is called a type, right? So we can count how many sequences in each type, and then we can add them together or whatever, So kind of we can do some precise operation here, okay? But in this class, we're not going to touch too much on this. In most of the theorem in our class, so we can show that using the entropy typical set, which is given by our textbook, the Thomas Cover textbook, okay? So we'll work on this, okay? And equivalently, it basically means that the probability of each sequence that in the typical set is given by this, right? Or that, they're like, yeah, we can think, this and that, they are pretty much the same, right? So epsilon can be arbitrarily small, right? So it basically means that the probability of each sequence in a typical set is given by 2 power n times minus n times hx, right? That's why it's called equipartition property, right? So the probability are equal for all the typical set. Okay, so that's basically the meaning of typical set. Okay, and then we can show that, so this typical set, which is a stronger version compared to the entropy typical set, is inside this, right? Which kind of makes sense, right? Because here we're working on each probability distribution, we're working on each probability value, and here work on the average sense, right? So, okay, and the approach to prove this is to use the so-called typical average lemma, okay? And this is kind of a very important lemma used in information theory, okay? And yeah, we just finish here. All right, so in this class, we're going to continue working on this. Mm. 32. Today is our lecture number 13. We have 2 topics for today. The first one, we're going to finish the AEP, especially we'll talk about the properties of AEP. Well, 4 properties to talk about. And then, so we'll start talking about data compression or source coding. Okay, so yeah, let's see the property of the typical set. Let's see, yes, here. The properties of a epsilon n. Right, I'll just use epsilon here instead of epsilon prime because from now on we'll just focus on this entropy typical set, right? We don't touch the other typical set. Okay, so the first property is kind of a trivial one. So the first property is that if our random vector x is in the typical set, and then obviously we know this. Okay, so the absolute value of this would be less than or equal to n times epsilon, right? So, is that right? Or is that obvious? Yes? No? How can we prove that? You know, the way that we can learn this kind of very abstract class is that every time we will see something, try our best to think what you need here, right, to prove it, right? Number one, the first thing we need is a definition of a typical set, right? And then think about what is the definition of a typical set, right? So if you cannot remember it, then just take a look, right? But the goal is to remember everything, right? So when you take a look at the definition of a typical set, then what do you find? Exactly, right? It's just a definition, right? Therefore, there's no trick here, right? So this, we can prove that, by almost nothing but the definition of the typical set, right? Just that, yeah, we define, if X satisfies this, then it's in a typical set, right? Obviously, that's the number one, the simplest property, right? Okay. And second property is, it's still, it's almost trivial if we take a look at the definition, but it worth to mention this. So the probability of that is almost 1, right? So 1 minus epsilon for n sufficiently large Okay, that's obvious. Right, the first, when you see this kind of thing, the first question we may want to ask is that what do we mean by n sufficiently large?
N
Yeah.
big enough so that the thing holds, right?
Okay.
Just n big enough so that the inequality holds, right?
The equality holds.
The inequality.
Yes.
Yeah.
Yeah, that's right. In other words, so basically we may think that this epsilon is a function of n, right? We may think, when n approaches to infinity, so this epsilon probably will approach 0. Okay, something like that, right? Or in other words, for any epsilon, we can find a n, large n, such that this inequality holds. Okay, very good. Yeah, so this is basically this, so who have learned analysis in math? Mathematical analysis, like 4 level. Okay. Yeah, it doesn't matter. So if you have learned that, you'll see, this language is spoken there all the time, right? But it doesn't matter. It's not hard. So yeah, we can. Yeah, let me write it down to see exactly what we mean by this, right? Okay, so yeah, from the theorem that we have seen in our last lecture, theorem from our previous lecture. So we can basically show that. So this holds, right? When n goes to infinity, the probability that this minus this less than epsilon, so that equals to 1. Okay, so this is by the law of large numbers. Okay, and we can see that, so here, so this set is nothing but our typical set, right? So this is the definition of our typical set. Okay, so now we just need to interpret this theorem, and then we have our result, right? So the interpretation of this is that, so this means, so this theorem basically means that for any delta, so any positive delta bigger than 0, right, there exists a knot such that for all n that is bigger than or equal to a knot, then this probability is bigger than 1 minus delta. Okay, clearly delta is function of n. Right, so this is so this and this are the same, right? So this basically saying this, right? So from now on, every time when we see this, so we just interpret it in this way. That clear? Okay, then we're done, right? So basically, we just need to let epsilon equals to delta. Okay, and then we have this bigger than 1 minus epsilon for n sufficiently large. Okay, very good. So this is second property. So this is relatively straightforward. And third one is harder. Okay, the third one is to give, yes?
Could you go back to the number 1? So that should be ix minus n times hx?
No, I move n here. Yeah, so yeah, here what we give you is that 1 over n is in front. Yeah, okay, so for the third one, so we want to see the cardinality. Yeah, question?
Oh, I think, yeah, I see what he's talking. I think there should be n times the big H for 1.
Wait, where?
If you move the n to the other side, like you divide by n, then you end.
Oh, yeah, definitely. Yeah, it's a typo. Good. Yes. That clear? Yeah, there's an N for sure. Okay, and the third one is to bound the cardinality of the typical set. Right? Okay, so what is the upper bound of it? We kind of mentioned that already, right? So the upper bound of it is sort of 2 to the power of NHX. Okay, but to be precise, so that is this value. Okay, it's almost the same as 2 to the power of n times hx. Okay, so it basically means that the size or the cardinality of the typical set can be very small, right? For example, if h is 1, right, basically, let's say if all x's are Bernoulli distribution with a half probability, right, and then h is 1, right? If h is 1, then the typical set is what? Covers everything, right? Yeah, which is kind of obvious, right? So why is that intuitively? So why, every element will belong in the typical set in that case? Yeah, because the probability is always 1 over 2, right? No matter what your times, it's just 1 over 2 more to the power of n. That's it, right? Obviously, any probability will, any sequence will have those kind of probability. Therefore, that covers everything, right? Okay, but when the probability distribution is not half, right, and then this h can be very small, right? In that case, so the cardinality of the typical set can be way smaller than the whole set, right? So which is extremely important for compression, data compression. Okay, so we're going to see why. But now let's prove it. Yeah, how can we prove that? Yeah, let's see whether it makes sense or not. And then we're going to prove another theorem that is very similar to that. So basically what we're going to do is as follows. So we can write 1 equals to the total probability, right? Okay. Okay, and then, so this is bigger than or equal to if x is in a typical set. I think that should be this. Okay. Okay, and then px, right? And then what do we have? I remember what we learned in our last lecture. So the probability, can we bound it? Right? Now we know so this x is in a typical set. Then what is the probability of it? We know that, right?
Is it 0?
Not 0. 2 power of this, right? Exactly, right? So we have a lower bound and we have an upper bound. Okay, so here what we're going to use is a lower bound. So we're going to add epsilon and then do this. So this is our lower bound. Okay, very good. So now this is the beauty of this inequality, right? So now all the elements are equal. Okay, and this summation basically we can, we can remove it by using the cardinality of the typical set. Multiply this, right? Yeah, because all px are equal, right? And then we can move this on the other side, right? So we can get this guy is bigger than, or is bigger than or equal to, oh sorry, it's less than or equal to. Yeah, we move this guy on the other side, right? So this should be less than or equal to nhx plus epsilon. Okay, and then we're done. Yeah, this is how we prove it. That clear? Right, pretty straightforward. Right, next, let's see whether you can show the next one or not, right? So the number 4, it's very similar to that. So basically, we have upper bound for the cardinality. Now we need a lower bound. Okay, then what is the lower bound?
The same thing but
almost. Very good. So basically, your mean is given by this, right? Almost. So there's a very slight difference. So we need to write this in front as well. Okay. Why we need that? So basically now what we need is the reverse relation, right? It's not this relation. So basically what we need is that we need to show, so this guy has to be bigger than something instead of equal or smaller than, right? Sorry, instead of equal or, so we have to make this guy bigger than something, right? How to make this guy bigger than something, right? In other words, we don't need to make that be bigger than anything, right? We need to make sure this guy is bigger than something, right? Bigger than 1, for example, and then we're done, right? How to make this guy bigger than 1? There's no way, right? But it could be very close to 1. Right? So what we do is that, remember, so what we have here for the second property, we have this relation, right? The probability that x is in the typical set is bigger than 1 minus epsilon, right? Therefore, we can basically write this guy is bigger than 1 or equal to 1 minus epsilon. Right, and this guy basically equals to this, right? So now we have this, on the other direction, right? Then we're good, right? Next, we need the upper bound on this, right? So we just use the other one, right? We use the lower bound for the other case, and then we use the upper bound of this case. So this is upper bounded by 2 power n minus hx minus epsilon, right? Okay, and similarly, this equals to the cardinality of this. Right, and then we're done, right? We just need to move this to the other side, right? And can get the cardinality of that is bigger than or equal to 1 minus epsilon. 2n hx minus epsilon. Okay, and then we're done. Right, so this 1 minus epsilon basically coming from the property 2. Okay, so this is a property 2. Right, that clear? Questions? Okay, the proof is very similar, right? We just need to use this in another way, the inequality in another way. Okay, and this is everything I want to cover for the AEP, and later on, so when we use it, we're going to cover the joint typicality, right? So basically it means that if we consider more than one random variable, then what should we do? Okay, but that will be on the later part of the class. Okay, so now we'll finish here, and then we'll talk some important applications of it. Okay, and let's do a brief summary. So asymptotic equipartition property basically means as follows. So we have the whole set, so that is our xn, right? This is a total data set, and inside it, so we have a typical set, right? So this is given by what we call that T, epsilon n, right? So this is our typical set, okay? And then we have inside of this, we have something even smaller. So that's what is we call that epsilon prime, A epsilon prime. So they are our entropy typical set, right? And from now on, we'll just focus on our entropy typical set, okay? For our entropy typical set, we can see that, so here we have this property. So the probability of that is bigger than or equal to 1 minus epsilon, right? And then we know the cardinality of it. Roughly speaking, it will be equal to this number, right? And the probability that x is in the typical set is this. Put a dot here means approximately equal, okay? Yeah, you can see that. So this is a total number, and for each number, we have probability. Therefore, this multiplied that is basically 1, right? Almost 1, right? So this also implies that if X is not in the probability that X is not in the typical set is basically less than epsilon. Okay, that'll be very small. Yes?
Is there any type of geometric meaning behind the
Geometric meaning.
on the atypical set or not?
What do you mean?
Is there any type of like can it be represented like thought of spatially? Or is that is there like a different way to think about it?
Not sure. Yeah, probably. I think for the discrete case, so we can somehow think it as a counting argument, right? So basically, we're count number of zeros and count of number of ones, right? If we imagine this as this typical set, right? But for here, it's just a probabilistic argument. But when we consider X to be continuous, then we can define, also define the typical set. Maybe there's some geometric interpretation of it, because in that way, so everything's continuous. We think in terms of the balls and so on. There will be some geometric interpretation. Yes. Yes.
So when we say that the probability of an entropy typical set is greater than or equal to 1 minus epsilon,
yeah.
Are we saying that for a sufficiently large n, there will be
yes.
an entropy typical set?
Exactly.
Okay.
Exactly. Oh, entropy typical set is defined for each epsilon, right?
Right.
Yes. Yeah. So when n is sufficiently large, then this epsilon would be very small. Otherwise, epsilon can be large.
I think just what's confusing for me is like the like when we're looking at it, it's like there are many entropy typical sets, right?
Yeah. For
So
each epsilon, there's one.
When we say the probability is greater than or equal to 1,
yes.
are we saying that
1 minus epsilon.
1 minus epsilon. Are we saying that for a sufficiently large n, there will be at least one entropy typical? I'm just confused.
Oh, no, it's a very good question. It's a reverse. So for each epsilon, and then we can find a sufficient large n such that, so the condition holds.
Okay.
Yeah, in the reverse way.
Okay.
Yeah, in the other way, of course, it's fine, right? For each, for a large n, then there will be a bunch of epsilon satisfy this, right? Then, for each epsilon, there will be like one typical set.
Okay.
Yeah. But in practice, how we think about this problem is that we always want epsilon to be very small, right? That's the whole point of this, right? So when epsilon is not very small, the upper bound, the upper bound of this probability and lower bound is very different, right? But when epsilon is small, then they are almost the same, right? So that's very important. Very good, very good. Yeah, this is very confusing. So hopefully, when we apply this, it'll become more clear, right? So hopefully we'll have time to apply this today. Okay, so now let's talk about data compression. So data compression is the first application of what we have learned so far. So we're gonna apply almost everything we have learned so far. Okay. So it's also called source coding, or data compression. So it's in chapter 5. Okay. Okay. So yeah, we kind of introduced you this before already. So we consider a DMS, so a discrete memoryless source. Okay. So basically, yeah, as a reminder, so we consider a bunch of discrete random variable, right? Those are IID. Okay. And so we consider for each guy, we'll have this PMF. Okay. So one good example is a Bernoulli source, right? We have Xi, so that will distribute it with a Bernoulli distribution, right? So we can think x1 equals to 1 with probability p, and 0 with probability 1 minus p. Okay, so now we consider a point-to-point compression system to compress this source, for example, a point-to-point compression. system. So a point-to-point basically means one transmitter, one receiver. So this is a point-to-point. Okay. So let's say we have a source like this, right? And then we have an encoder. So we kind of have seen this before when we talk about the data compression inequality, right? So this is exactly that case, that scenario. So here M is our code word, right? So this is our source information. So now we'll assume the source information is like this. They're all IID and all 0 and 1s, for example, right? It could be other symbols, but as long as it is IID, then we're good. Okay, normally in our class, so we always consider that's like all 0 and 1s, okay? And then we map that to another code word, which is M, okay? And then, so we need to, once we see M, then want to decode it, right? Want to recover whatever is here, okay? And so we basically have our decoded signal, so that's X hat. Is that clear? Okay. Yeah, let's see. Okay, so in particular, we consider a very specific source coding here. So we consider a lossless, for now, block coding, block source coding. Okay, so lossless, this basically means it's a symptotic lossless coding. Asymptotic. So this basically means that, so the error is not exactly 0. The error basically means that the probability that this guy and this guy are not equal, right? So the error is not exactly 0, but will approach to 0 when this n goes to infinity. Okay, so we'll talk why we need that later. But this is the assumption. Okay, and the other thing is block. Okay, let's see what does it mean. So basically, the meaning of it is that basically we're going to fix n, and we map this length symbol to some code word. Okay, that means block. So we're going to code it block by block. The length of the block is n. Okay. So in practice, we don't always use block code. Okay, the reason we use block code is that it's very easy to analyze. Okay, so you'll see why. Okay, so let's give you a definition. What is a source code? Okay, so now we'll give you intuition, so what we want, right? But now let's see mathematically how can we describe this problem, right? And this is one of the most important, purpose of this class. Okay, how we can formulate a problem in an information theoretic manner. Okay, let's see how we can formulate the problem. So we let this set X to be the source alphabet. Okay, and we assume Y to be the code alphabet. Okay, so this is a given, right? So all our source symbols, and this is up to design. Okay, we can design this. All right, so we say a calligraphic I, and this means the cardinality of I. So this n source code consists of the following functions. Okay, the first function is the encoding function. The first function is an encoding function. Okay, so encoding function is a function f that is a map from our source alphabet to our code alphabet. Okay, and the length here is n, and the length here is m. Obviously, m and n are not equal in general, right? Otherwise, why we do that? Okay, and so this set, product set, or Cartesian set, so a Cartesian product, so that will give you the the set of I, right? So the I is a set of all the possible code word, right? Does that make sense? Okay, and obviously if you want to label them, so the symbol is from 1, 2, up to the cardinality of I. Okay, so what, yeah.
What's A again?
What is
A?
I mean, it's a,
A of,
yeah, it's A means singular.
Okay.
Yeah, not a set. A source code means that. Okay.
Got it.
Yeah, because we may have many source code.
Yeah.
Otherwise, we will write the source code. Okay. Yeah. Maybe I'll write it smaller, so to not confuse you. Yeah. A source code. Okay. Yeah, it's not a symbol. Sorry. Okay. So these are encoding function, right? So so why we call block code is because of this, right? So we code all n together, not one by one. Okay. All right, and then we have a decoding function. Decoding function, we denote it by G, right? So the function of that is also very simple, right? So basically, that is to map. Not this. That is to map from I. So I is our code word to what? Our original alphabet. Okay. Right, and then, so this is definition of a code word, of a source code, right? It's just a mathematical description and then make it more rigorous. Okay, so now we have an important observation, right? So if the cardinality of I is less than the cardinality of this guy, or the cardinality of this guy, so that equals to the cardinality of this, right? So if I is less than the cardinality of the source alphabet, then what will happen? Yeah, right. So let's say, so here, we have, this is all the possible source alphabet here, right? And we map it here. Okay, yes.
You would have collisions, right?
Yeah, so we use a different word here. We have error, right? Collision basically means that we have to have like a multiple to one mapping, right? Then we definitely have error, right? Because we don't have enough number, the size of the alphabet, right? So very good. Then the source, then some words will be recovered incorrectly, right? This introduces a very important concept of error, right? So now we need to define it. Okay, we define x hat n, so that is g of f n, right? So that's the decoded code word. And then we denote error as PE, so that equals to the probability that x n and x hat n, so that are not equal. Okay, so that's the definition of the error. Okay, and then we can define the rate of a source code. Okay. A rate R. Yeah, okay. Yeah, let's write it in a different way. Let the rate R be the number of bits per source symbol. In other words, so it defined in this R equals to log base 2 cardinality of I over n. Right, so it basically means that if we want to represent the cardinality of the the code alphabet, then how many number of bits we need? Okay, and over n. All right, so this is a rate, definition of the rate R, and definitely we want rate to be less than 1, right? Otherwise, there's no compression. Okay, and now you may ask, right? So if we want this number to be less than 1, it basically means that we are in this region, right? The cardinality of I has to be less than the cardinality of the source alphabet, right? Then we definitely have error, right? That's why here we assume that the lossless is asymptotic error 0. It's not exactly error 0 because in this setting it is impossible. Okay, then but what we can show, what is possible is that so the error can be arbitrarily small. Okay, so it's still a lossless code. Okay, so yeah, let's define it. So we say a rate R is said to be achievable if there exists a sequence of this codes such that this probability will approach to 0 as n goes to infinity. Does that make sense? Right? For each n, we can design such a code. Okay, and when n approaches to infinity, and then so this error will goes to 0. Okay, so this is the definition of the error and the feasibility of a code. Yeah, let me write one more sentence, then we can answer questions. So we define R star as the infimum of all achievable R. Okay. Yeah, one more thing here to be noticed is that so it's the infimum, it's not the minimum, because this R may not be achievable by finite n, right? So it can be achievable if you allow an arbitrarily, epsilon. Okay, so this is tricky, but we're gonna see what we mean by that exactly. Okay, and then this is we finished the definition of a code. Okay, so from here, from here, so we describe encoding function, decoding function, and then we define what is the error, and then we define what is the rate, and then we define, okay, what is the achievable rate, and then we say, okay, we basically want, the infimum of all the achievable R. Okay, so that's the best we can do. Okay, so we're gonna see this kind of definition again and again. So this is the kind of information theoretical words. Yes?
Okay, so n is the length of the source code, right?
Yes.
And then m is the length of the code word, or m is the length of the code word, right?
Yes.
And they're unrelated. Like the definition of m does not change the definition of m, right?
Yes.
Okay. So then how come when we increase the length, like as n goes to infinity, we're making the length of the source code longer? Why would that cause a probability of error to go down?
Yeah, you'll see.
Okay.
Yeah, so we're going to explain that.
Okay.
Yeah, very good question. Yeah, definitely we should think in that way. Okay. Yeah, probably you can, I see, yeah, probably you know that already, right? Probably you can think, why we want to introduce you all kinds of the concept before, right? Did you see anywhere n goes to infinity, right? You see that all the time, right? What happened? Right? What happened when n goes to infinity? Some concentration will happen, right? And then we have a typical set magically, right? What is typical set? It almost cover everything, right? That's why basically. But we're going to say that in very detail. Yeah, very good question. Okay, great. Okay, so now, yeah, we have 5 minutes left. Let me write you the most important theorem in the entire information theory, right? So for information theory, for Shannon, you may heard of, we have the Shannon first coding theorem, Shannon second coding theorem, Shannon third coding theorem. I mean, from Shannon, it's like we have 3 important theorems in total. You know, somebody compare that to the Newton, the 3 laws. Okay, so now we're going to introduce the first one. Okay, Shannon's first coding theorem. Okay, or people call that lossless coding theorem. Lossless source coding. Theorem. Okay, let's see what is that. So the optimal rate, by optimal we mean the smallest or the infimum of all R, right? The optimal rate for lossless source coding of a DMS, discrete memoryless X, is given by this R star. So that equals to, probably you can guess it already, right? Entropy. Okay, so entropy is the best we can do. Okay, so any question for this theorem? Right, given all the definition here, R star exactly means this R star, right? So the best we can do is entropy, right? So basically, let's say if we have a length of n for the source code, the best you can do is n times entropy. So that's the number of bits you will transmit. The best you could, yeah, for almost 0 error. Okay, so let's see how we can prove that. Again, so this proof is extremely simple, but it's very, very typical. It has almost all the important ingredients for all the complicated information theoretic proof. It's just the most simplest version of it, but it has everything. Okay, so let's see the idea of the proof, right? So normally information theoretic proof, we need to 2 parts, right? You can see here we have an equal sign. So means R star equal to that, right? Equal sign basically means that, so usually we can now say something equal to something, right? So what we're going to do is that we're going to show an upper bound on our R star, okay? And then we're going to show a lower bound of R star, and we show they are equal, okay? And the upper bound is easy to understand, right? We just say, okay, this is less than something, right? Using some whatever inequality, right? But the tricky part is the lower bound. What is the lower bound? It means that we need a scheme. So we need to construct a coding scheme to show this R star is achievable, okay? So that's basically how we do it. Okay, let's write it down. So number 1, so we need to show the achievability. Okay, so what we mean by achievability is that we're going to show a real code with this coding rate. So we're going to allow an epsilon there, right? Because it's the infimum. Basically means that for any finite n, so we allow a margin of epsilon. Okay, so for R is less than this guy, so for any R epsilon R, so we have to show that this guy will goes to 0 when n approach to 0, approach to infinity. Okay, so this is the idea for the achievability, and then we need to show an upper bound of R here, right? So this upper bound, we call that converse. Converse basically means the impossibility. Okay, and in this case, yeah, did I say any upper bound? I mean, it should be lower bound, right? Because it's a source coding problem. So we show R will be bigger than or equal to hx minus epsilon, right? Again, we allow a margin of epsilon. Why we want to show it's a minus epsilon, not plus epsilon? Because make it smaller will be just easier, right? Make it plus epsilon may be impossible. Okay. So we say R is bigger than this guy. Okay, again, so yeah, in order to distinguish between this epsilon and this epsilon, they could be different, right? We just write the epsilon prime here. Yeah, for all epsilon prime bigger than 0, again, so this has to go to 0 when n goes to infinity. Right, this is very important. Okay, so let's see. Okay, so we're kind of over time already. In the next lecture, we're going to finish the proof. You'll see how we prove that. Okay, very good.